Hi, in this video we will look into parsing arithmetic expressions. So arithmetic expressions actually is the most studied aspect when we look into a programming language. We have looked into a lots of arithmetic operations when we do a programming. Let us consider the grammar G5. In order actually to do a parsing for a grammar, we want to know actually first we need to identify whether the grammar is in the LL1 form or not. Okay, so let's look at the grammar G5. This is the grammar for arithmetic operations. We want to determine first what would be the selection set for this grammar. So in order to know that, to find the selection set, we have to apply the 12 steps rules, the 12-step algorithm that we have looked in the previous video on the LL1. Okay, let's look into the steps. Okay, step 1 is to find the nullable, okay, nullable rules and also nullable non-terminal. Okay, for this grammar G5, there is no nullable rules, there is no nullable non-terminal. Okay, then we want to find what will be the selection set of it. Okay, then we move to step number 2. We find begin directly with, which is a BDW for each of the grammar that we have here, the rules that we have here. Okay, so BDW for the first rules is expressions, okay, which is the first one here. BDW for the second one will be term. The rules number 3 is also term. Rules number 4 is factor. Rules number 5 is the open bracket, and rules number 6 is var. Okay, that is the BDW for each of the rules. In the next steps 3, we want to find a begin with. So begin with actually is to find the reflexive transitive closure. Okay, so here is the answer. To find the reflexive transitive closure, then there are 3 parts of it. We have to copy the first BDW from the previous steps, and then we need to find, in this case this is the reflexive, and then the last part here is the transitive. Okay, the transitive. This is from BDW. Right, so that is the steps 3. Okay, now is step number 4 is to find the first x. First x actually to get the terminal. X is the terminal. So the result that we get here is actually from step number 3. So this is the result from step number 3. I copied it in this slide. Okay, for first expressions, we have to look into the expressions on the first string here. Okay, the first rules, second rules, third, the one that I highlight here. Yeah, so all this is the expression, but we only interested in the one that begin with terminal. Okay, if you look into this 5 pair of expressions, the one that actually begin with a terminal is on this one, the open bracket. Okay, and then also a var. The rest of it is in the forms of non-terminal, so we are not interested in that. Okay, so we took open bracket as well as a var as a first EXPR expression. For first term, it is the same process. We have to look into the term in the step number 3. So term that I highlighted here is 1, 2, 3, and 4. Okay, so among these 4 pairs, so we have to look at the one that actually begin with a terminal. So it's open bracket here as well as var as well. So the one that begin with non-terminal will be cancelled off. We are not interested in that. The same thing as factor. So we look into the factor. For the factor, we have 1, 2, 3 factor. okay, but we're interested in the one that with a terminal, so open bracket var, and the factor we are not interested in. So the first for factor is also open bracket and var. Okay, in this case it's similar for three of them. Okay, moving forward to step number 5. So we using a result that we get from step number 4, but this time we want to find the first for each of the rules we have here. Okay, for example, the first rules in this example is the expressions. So first exp plus term. So what we get actually is open bracket and var. Okay, for first term we get open bracket and var as well. First terms times factor also we get open bracket and var. Okay, for the detailed process you can look into our previous video on the LL1, yeah, for the detail how to get it for each um, of the rules here. We need to have a union operations, something like that. Okay, so this is the result for what you call the first for each of the rules, step number 5. If you look into what we get here, there is no nullable rules. Okay, there is no nullable rules in the grammar, so actually we can obtain the selection set directly from the step 5. So this would be our selection set because there is no nullable rules. Okay, so this would be our selection set. We already get our selection set in these steps. Now we jump directly to step number 12 because we don't have any nullable rules and no nullable rules. So we jump to steps number 12. However, our purpose just now is to check whether the grammar is in LL1 or not. But in this case, we see that actually this grammar is not in the LL1 because why? Okay, so I state here the reason why it is not in the LL1. To be in the LL1, actually, we cannot have the intersect of selection set. Means that if you have a non-terminal, the same non-terminal cannot have the same selection set. That is what it means. Okay, but in this case, if you refer to rules number 1 and rules number 2, so they actually define the same non-terminal, which is expressions. Okay, which is expression. Okay, first one and second, which is expressions, and they're actually having the same selection set, which is open bracket and var. So this will indicate that actually this is not in the LL1 grammar. Okay, this is also true for rules number 3 and also rules number 4. They are actually the same non-terminal. Okay, but they actually have the intersect selection set as well, the same selection set as well. So we say that this grammar is not in the LL1. Okay, so grammar G5 is not suitable for top-down parsing, so it can be determined actually much more easier by inspecting of the grammar. Okay, in other way to inspect it whether it can be used for a top-down parsing or not is actually by inspecting the grammar itself. Okay, let's look into the grammar 1 and grammar 3. Okay, so both have a property known as left recursion. Okay, left recursions means that on the left or on the beginning of the right hand side here, they actually have a non-terminal. Okay, they have a non-terminal. So we say that it is actually not suitable for top-down parsing. Okay, instead of finding using this the 12-step algorithm, we actually can determine it earlier on the grammar itself. Yeah? When you see if the grammar have a left recursions, means that it is not suitable for top-down parsing. Okay, that is another way to look into it. Okay, so any grammar with a left recursion cannot be LL1. So that is another way to determine whether the grammar is not is in the LL1 or not. Okay, so by using the 12-step algorithm, or you can see on the left recursions. So two ways to determine whether the grammar is in LL1 or not. Okay, now we already know that the grammar G5 is not in LL1 because of the left recursions and they have the same intersect selection set. How are we going to make it become a LL1? So there is a way, we call it, we want to eliminating left recursions. Okay, so how to eliminate the left recursions? We have a general rules here. We have like A goes to A alpha, A goes to beta. So A here is a non-terminal. In this case, in the G5, it will be expressions. If you look into the rectangle, okay, let's say we consider that in these explanations. A here actually will represent expression, EXPR. Okay, alpha in this case is a term, a plus term. Okay, it's a plus term, and a beta here is actually term on the down here. Okay, this term, the second rules. Okay, now we have, that is the general rules that we have. So how to eliminate the left recursions is by introducing a new non-terminal. Okay, let's say we call the new non-terminal R. Okay, so we're rewriting the rule as A goes to beta R, R goes to alpha R, and R goes to epsilon. Okay, so we going to rewrite the general rule we have into new rules. Okay, this is the way, actually this is the process to eliminate the left recursions. So what will we get? Okay, let's look into number 3. So the new rules after eliminating the left recursion for G5. Okay, so in here we want to introduce a new non-terminal called Elise. Okay, remember it's steps 2. In order to eliminate the left recursion, we need to introduce new non-terminal. Okay, so in this case for G5, we will introduce a new non-terminal called E-list. E is expression, expression list. Okay, so how? So we follow the format we have in the second steps here. Okay, A will be the expressions. Okay, so beta here is term. Okay, we replace the beta with term. So we replace R with ELIS. Okay. Okay, second is R goes to alpha R. So R actually is ELIS. Okay, alpha is actually plus term, and R is ELIS again. Okay, now we move to the third one. R goes to epsilon, so our third rules will be ELIS goes to epsilon. So this is the step to eliminate left recursions. Okay. Okay, now we will be doing the same process. Okay, the same process here for rules number 3 and as well as rules number 4. Okay, rules number 3 actually refer to the general rules. Okay, A here actually is the term. Okay, alpha is actually a multiple factor. Okay, and a beta actually is a factor. Okay, so bear that in mind. So we're going to eliminate the left recursions and convert it in this form. Okay, the second form. Okay, so the new rules will be, okay, the first one is our new non-terminal, we call it as a T-list. Okay, so look at the first rules. A goes to beta R. So A is a term, beta is factor, and R is our T list. Okay. Second one, R goes to alpha R. So R actually is a T list. Alpha actually is a multiply factor, and R is a T list. The third one, R goes to epsilon. Okay, now R actually is a T list, goes to epsilon. Okay, this is how. Yeah, that is the steps. We do it for the first, second, third, and fourth because of if you look into the rules, they have a recursive. Recursive means that the term will be looping. We'll call it back again and again. They call the same non-terminal again and again. For example, the first rule, expression goes to expression plus term. Actually, the non-terminal is expression. It will call expression again and again, means that there is looping there. So we want to remove that recursion actually. Yeah, that is why we didn't do it for 5 and 6, because 5 and 6 does not have any recursions on the rules. Okay, now we look into this is the new grammar G16. After we have eliminated the left recursions, so this is what we get actually, okay, for the G16. Okay, now after we have removed the left recursions, we want to check it once again whether this grammar actually is the LN1 or not. Again, we have to do the 12 steps algorithm in order to determine whether the G16 is in LL1 or not. Okay, so this is the result after you have conducted the 12-step algorithm. I did not show the step-by-step process, so I assume you already familiar with the steps. If you are not familiar yet at this stage, you can refer to a previous video on LL1 on the 12 steps, LL1 part 1 and as well as LL1 part 2, okay, for the step 1 until steps 12. So here I only show you the last output for steps 12 for the G16. Okay, so this is what we get for the selection set for each of the grammar, for each of the rules in grammar G16. Okay, so if you look into this selection set for each of the rule, we see that since all the defining the same non-terminal, the rules that defining the same non-terminal, which is rule 2 and 3, 5 and 6, 7 and 8, all have a disjoint selection set. Means that they did not have a similar selection set. Did not the same. It is not same. Means that rule and 3 will have different selection set. 5 and 6 will have different selection set, even though they have the same non-terminal. So in this case, we say that this grammar G16 is in LL1 form. Okay, we already know that G16 is already in the LL1 form. Now we can construct an extended pushdown machine for the grammar G16. So actually the process for constructing the pushdown machine is similar to the one that we looked in the previous video on LL1. Okay, the step is the same. So you can use the output that you get from the selection set that you get from step 12 to fill up this table. Okay, for examples, you have a selection set for rule 4, you have open bracket and var, so we can fill the cell in the row label term, okay, in the row label term, and the column open bracket as well as var. Okay, so which is here with the rules on the right hand side. Okay, which is we replace T list vector and retain for both open bracket and var input variable. So it is actually the same way that you construct a pushdown machine in the LL1 in the previous video. Once it is in the LL1, you also can construct the recursive descent parser, okay, for the grammar. So constructing recursive descent parser is also the same step, the same way that you have learned in the previous video in the LL1. Nothing different. It is similar. Okay, so you have to construct for each of the non-terminal that you have in your code. Okay, it will be based on the each of the rules for each of the non-terminal. Okay, and you need also to use the selection set that you get from the step 12 in the G16. Okay, for example, I give here for the first rules is expressions. Okay, under the expressions, you need an input open bracket and var. Okay, for example, and next the process is term and then elist. That is the first rules. Okay, else it will reject. So it actually will be the same for the rest of the rules that we have. Uh, only one thing, if you see a follow statement like a selection set number 3 here, okay, if you see a follow, then you will do something like this. Else if input is a close bracket and also the input is the end marker and you do nothing. Okay, for follow you do nothing. Yeah, so you straight away put a semicolon there, means that you do nothing in that particular fractions of code. So this slide is the continue from the recursive descent parser for the rest of the rules. Okay, we have a selections 4, 5, 6, 7, and 8. So here I share how the code looks like for each of the rules. You can have a look. As I said, is a same way that you construct it in the LL1 grammar in the previous video. So we come to the end of parsing arithmetic expressions top-down. So in this subtopic, what you learn actually is to be able to identify whether the grammar is in LL1 or not. If the grammar is not in the LL1, then you need to remove to identify the left recursions and remove the left recursions. Okay, when you remove the left recursions, you need to introduce the new non-terminal, okay, in order for you to remove the left recursions. After you have removed the left recursions, you need to recheck again the grammar, the new grammar, whether it is in the LL1 or not. If it is in the LL1, then you can continue by constructing a push-down machine as well as the recursive descent parser. Now we move to the next subtopic, which is on the syntax-directed translations. In the previous subtopic, we have a look into the top-down parsing for a quasi-simple, and for LL1 grammar. Okay, those grammar actually can only check for the syntax error, but not on the semantic error. Okay, semantic error is on the logical error of the program code. Cannot check. It only can check on the structure. Okay, the previous grammar that we learned also cannot produce an output. We cannot check the output as well. Okay, so in this subtopic, okay, we want to introduce what we call an action symbol, which are intended to give us the capability of producing an output from the grammar that we have. Okay, so a grammar containing action symbol, we call it as a translation grammar. Okay, so the next grammar that we're going to learn is called a translation grammar. So this translation grammar actually contain action symbol. Now we look further into what is a translation grammar. So inside the translation grammar, we have what we call as an action symbol. So action symbol in this grammar will be represented using a curly braces. Okay, you will look into the grammar. Inside the grammar, when it has a curly braces, it is actually an action symbol. Okay. Action symbol actually is to produce an output. Actually, is the output of your grammar, of your programming. Okay, so if you need to find the selection set, okay, bear in mind, if you need to find the selection set for translation grammar, you must remove the action symbol first. Okay, that is the rule. If you need to find the selection set, you must remove the action symbol. So how do you know which one is action symbol? Action symbol actually is indicated or represented using a curly braces. If you look into grammar G17 here, if you look into rule number 2, there is one that I underline here is action symbol, and then another one on the rules number 5, and another one in rules number 8. Okay, so that is a action symbol. It's an output of the program. Okay, when you want to find a selection set, you need to remove it, delete it from this grammar. So when you remove action symbol, okay, the new, not say the new, the one that without the actions symbol is called underlying grammar. We call it as an underlying grammar. In this case, G17, we remove the action symbol. Actually, this translation grammar come from G16. Okay, we add action symbol to the G16 and it become translation grammar. So the one that without the action symbol, we call it as an underlying grammar. Okay, now we look into the example on the translation grammar. We have a G17 as our translation grammar. Okay, so in this example, we're going to translate infix expression involving in addition as well as a multiplication to postfix expressions. Okay, from infix to postfix expression. And so this is our G17, okay, grammar, the translation grammar. Okay, we want to be able to do a derivation 3 for the expression var plus var multiplied by var. So this is output that we want from this translation grammar. Okay, using the G17. So we start by deriving the derivation 3. We start with the first rules, which is expressions. Expressions we goes to term as well as e-list. So this is actually from the first rules. Okay, and then from the term itself, okay, we use rule number 4 to get a factor and t-list. From the factor, we choose, there are two there, factors number 7 as well as number 8. So because the derivation that you want is to be able to produce var plus var times var, so the next derivation will start with number 8, factor the rules number 8, var, and in the bracket, curly bracket, another var. Okay, means that we also represent the output. We also represent the action symbol inside our derivation 3. Okay. The next process is to derive the one in e-list. Okay, under the e-list, we have here is the plus terms on the second rules here. We use the second rules because of the language that we want to derive, the expression that we want to derive is var plus var first. Okay, we want to have addition first, so we choose rules 2 instead of rules number 5. Okay, then we do the derivations for terms. Terms is factor and t-list, and factor again we choose var and var. Okay, so here another output, another action verb here. Okay, and we continue the process until we get to the end of the expressions, which is var plus var times var. Okay, so the output that we get from this derivation 3 from this grammar G17, if you can write it from this left hand side, is var plus another var here, okay. We look into the output, yeah, or the action verb, okay, and then the multiplication sign, and then the addition sign. So this is actually in the forms of postfix output. Okay, so this is what we want to get from this translation grammar. We want to be able to produce postfix output when we insert the expression var plus var times var. This is our infix input, and this is the postfix output that we can obtain from these grammar translations. Next, then how are we going to implement the translations grammar with a push down translator? Okay, we want to construct a push down translator for these kinds of grammar, translation grammar. So the first one is action symbol should be treated as a stack symbol. Means that it is actually a stack symbol. Okay, in the push down machine we have to stack symbol and input symbol. Okay, so stack symbol is on the row side, input symbol is in the column, so we put it in the column normally. Okay, so action symbol, because it is a stack symbol, we represent it it should be in the row. Okay, it should be inserted into a row of the push down machine table. So every column of that row should contain the entry out A, pop, and return for that particular cell. So for each of the column, okay, we should put out A, pop, return. Okay, so the pushdown machine is then called extended pushdown machine. Here is the example of extended pushdown machine for G17, grammar 17. We have a translations grammar here. Okay, so the rest actually of the grammar, we construct it as the same way as the other pushdown machine in simple grammar, on the quasi-simple grammar or LL1 grammar. Okay, it's the same way, except that for the green rectangle here is extensions or an extra informations about the action symbol. Okay, we add another information on action symbol, which is placed on the bottom part of the pushdown table. So we insert there are 3 action symbol in this grammar G17, which is var, multiplication, and addition. So we put it here. Okay, so the symbol actually inside the curly bracket. Okay, it is actually different from the one that on the top here. Okay, because this is not an action, this is actually the string inside the grammar, but we add another action symbol which is in a curly bracket for an action symbol. Okay, so it says that for every column of the pushdown machine, we need to put pop, return, and out variable if it is variable. If it is addition, then pop, return, out, addition symbol. Or if it is a multiplication, then we put pop, return, and out, multiplication symbol for all the cell, for all column, okay, for the action symbol. Okay, this is how we construct extended pushdown machine for translation grammar. The next one is to implement the recursive descent. Okay, so recursive descent is actually having the same steps as well as the one in LL1, except for the one with the action symbol. Okay, let's say we consider grammar 18 here. We have S goes to print AS. Print is the action symbol. S goes to BB and B goes to print. Print here is the action symbol. So how would it actually represented in the recursive descent code? Okay, so for every action verb, you need to put a system.out.println because action symbol actually is an output. Okay, in an output. So every time you come across the action symbol, you just need to put a system.out.println. Whatever the action verb it is. Okay, in this case it is print. Okay. Okay, now this is for G17. Okay, how are we going to write the recursive descent translator for G17? Okay, for G17, we have like in the second rules here, we have an action symbol plus. Okay, action symbol plus. So we just add a code system.out.println plus. Okay, for the rules number 5, we have action symbol multiplication. So we just add a system.out.println multiplications. And the last one is rules number 8. We have action symbol var. So in our code, we just add system.out.println var. Whenever we see action symbol, we just write system.output.println. Okay, remember, because the action symbol actually is the output. In this slide is just to show you some exercise on the how to construct a pushdown machine pushdown translator for grammar G18. This grammar is quite simple, so that you can see it clearer how to actually construct it. Whenever they have an the first one is you need to enter the action symbol, okay, print inside the row. Because action symbol actually is the stack symbol, so you put it under row. Okay, and so each of the cell, each of the column for the action symbol, you need to write pop, return, and out. Whatever the action symbol is. In this case, the action symbol is print, then you write there out print for each of the column. Okay, the rest will be the same as the one in LL1. So that is the end of syntax-directed translation. So in this subtopic, you have been introduced with a new grammar, which is translations grammar. So in this grammar, you are introduced with the action symbol. So what is action symbol? Action symbol is actually the output. Okay, you actually represent output in your grammar. Okay, next subtopic is on attributed grammar. Okay, so the attributed grammar is actually a context-free grammar with the additions of attribute and attribute evaluations. Okay, so they add on attribute and attribute evaluations. Okay, this is another grammar, attribute grammar. We call it attribute grammar. So actually this attribute grammar can specify both semantic and syntax. Okay, while the previous one, they only can detect syntax only. Okay, so this attribute grammar is introduced to actually so that we able to specify the semantic error as well. Okay, instead of just a syntax error. So each of the terminal and non-terminal may have 0 or more attributes. So means that we, with the underlying grammar, we want to add some more information about the attribute. Okay, about the attribute. So the attribute normally is designated by subscript. So we represent the attribute using a subscript. So there are two types, synthesized and as well as inherited attributes. There are two types of attribute grammars. First one here, we want to look into a synthesized attribute. Okay, uh, we can see the example here, G19. Okay, for the examples of attribute grammar. Okay, normally attribute grammar will have a subscript, like in this case, EXPR. They have a subscript of P. Okay, and then they have attribute value of P goes to Q plus R. Okay, so this is examples of attribute grammar. So what about a synthesized attribute? Okay, synthesized attributes means that when we create a derivation tree, we normally include the value inside our derivation tree. Okay, like for this example, if you have a prefix expression plus multiple 3, 4 plus 5, 6, so we will insert this value inside the derivation tree. Okay, for example, we have a plus multiplication constant. The first constant is 3, and then the second constant is 4, and then plus, next constant is 5, and then next constant is 6. Okay, so what does it mean by synthesized attribute is the sub expression, the sub leaf here, okay, the sub tree here will take the value from its lower knot. That is synthesized. Okay, means that in this case the lower knot here is constant 5 and constant 6, so the upper knot will take the summation value, which is 11. So this is what we call a synthesized attribute, means that it takes the value from the lower knot. Then another one is inherited attribute. So inherited attribute is on the other way around. Okay, let's say you see these examples on a grammar G20 is on declarations. Okay, declarations of variables. So what we can see here, if inherited, it actually get the value from the upper knot, a higher knot. Okay, for example, in this case we want to declare variable a. Okay, variable a, so actually variable a will be depends on the type on the higher knot, which is in this case is integer. So this variable actually will depends on the higher knot types, which is integer of a. So this is what we call is an inherited, means that the value of a will depends on the upper knots or the higher knots of the derivation tree. So that is the end of attributed grammar. We will look further on this attributed grammar in the next video. So in this video is just an introduction of what is attributed grammar. So attributed grammar is a grammar with add-on informations on the attribute of the grammar itself. So we will continue to look further into attribute grammar in the next video. Thank you very much.